Our next speaker is a PhD candidate from Laurentian University and a researcher at the Center for Research in Occupational Safety and Health. Her name's Katie Goggins, and she's going to be speaking about vibration-induced whitefoot. So, Katie?
Okay, good morning, everyone. Like Trevor said, my name's Katie. I'm a fourth-year PhD student, or candidate, I guess, and I'll hopefully be defending at the end of this year. My PhD is in Natural Resources Engineering out of the Barty School of Engineering, and today I'm going to be talking to you about vibration-induced whitefoot. So as it's a really specific occupational hazard, I'm going to run you through a bunch of background information. We'll talk about the symptoms, how we measure vibration, and then we're going to talk about 3 of my research objectives from my PhD. So just to start, typically occupational vibration exposure is categorized by the contact point with the vibrating source. So for whole body vibration, the contact point will typically be for a seated person. It would be at the buttock and the lower back of the seat. For hand transmitted vibration, it'll be at the hands. So people who are operating any kind of drill or chainsaw, anything that's vibrating in their hands. And then for foot transmitted vibration, which is the main topic for this presentation, it's any kind of platform or anything that a worker might stand on where the platform's vibrating and their contact point will be specifically at the feet. So what are the kinds of health effects that happen from vibration exposure? For whole body vibration, you're going to see spine disorders. So this could be things like disc herniation or anything to have to do with the lower back and spine. You can see some neck and shoulder problems, anything from rotated postures while seated. You could see gastrointestinal disorders or any kind of reproductive effects. We also will see auditory effects from vibration exposure here. For hand-transmitted vibration, it's more of a combination of osteoarticular, neurological, and vascular disorders. These could include vibration-induced white finger and vibration-induced white foot. So you're going to see these two have been, hand-transmitted vibration and foot-transmitted vibration have been coupled together here just because the symptoms are so similar for both of these anatomical areas. And since there's a lot more research done on hand-transmitted vibration and there's a lot more documentation of the symptoms and the health effects with regards to the hands instead of the feet, I'm just going to run you through very quickly kind of the symptoms for hand-transmitted vibration exposure. So there's 3 different systems that are affected. One of them will be the nervous system, and this will be the nerves. In this case, in this example here, you'll see that this is an example of carpal tunnel syndrome. So the carpal ligament, the carpal ligament here will become inflamed or swollen, and then that could cause a compression syndrome on the median nerve, and then that's going to result in a loss of sensation to the fingers and thumb, and this will be a loss of sensation or touch or temperature, and that's just the nerve damage that could happen from prolonged exposure to hand-transmitted vibration. Then we can see things such as, so this is more what the talk is about, is the vibration-induced white finger. So this is a vascular system, and here you'll see what happens for vascular effects. It's, in the end result, it's a blanching attack, and that's on the right here. You'll see the whiteness in the fingertips, and that results from any kind of damage to the arteries. So here you'll see what would be a normal artery, and then blood flow to a damaged artery. It just the artery becomes constricted, and then blood flow to the fingertips is restricted, and that's what's causing the blanching effect. And this can be brought on by prolonged vibration exposure, or by even just going out in the cold will trigger an attack. Another system that could be affected is musculoskeletal system. So you could see things such as tendinitis. So this is just an inflammation of any of the tendons, and this could cause, for hand-transmitted vibration, could cause things like reduced grip strength for people who are holding on to tools. And then you can also see with joints, you can see arthritis or contracture. So contracture is just an inability. If you've ever had your fingers lock up and you can't straighten them, that's what contracture is. So then I just want to run you through the symptoms, because the symptoms are very similar for foot transmitted vibration exposure. It hasn't been researched as well, but the symptomology is very similar. You'll see neurological symptoms first, so there could be numbness and tingling in the toes. There's a reduced sense of touch and temperature with neurological symptoms. The vascular symptoms, we could see an increasing loss of circulation and toe blanching. And then osteoarticular, again, we could see bone or joint damage or muscular fatigue in the legs or lower limb. And on the right here, we just have what would be kind of how a blanching attack would happen in the toes. So at first, the loss of circulation to the toes would cause the toes to go white. And then they would progressively turn either a purple or blue color. And then about 15 to 20 minutes later, they're going to turn kind of a red color when the blood flow continues to go back to the toes. And then this is just an image of prolonged exposure. What could happen when this is necrosis. So those last two toenails, this is necrosis. This is extremely permanent damage. There's no way to get the circulation back to those toenails. So eventually what could happen is amputation. Then I just want to talk about how do we actually measure occupational vibration exposure. So there's a couple of different standards that we use. For whole body vibration, one of the international standards, it's called ISO 2631-1. And then this was typically for seated operators, and we'll use the most dominant axis, which will usually be the vertical axis. And you get at the end of the analysis, you'll get an A8 value. You're going to compare this to the 8-hour health guidance caution zone, where anything above 0.9 would put a worker at an increased risk for vibration-induced injury. And then anything below 0.45 would decrease the risk for the worker. For hand-transmitted vibration, we also have an international standard. It's ISO 5349-1. So here, this uses a total sum of all the axes. And you're going to get what's called a vibration total value. So it'll sum X, Y, and Z. You don't have to worry about dominant axis. And then any value greater than 2 is associated with an increased risk for hand-arm vibration syndrome. So any of those symptoms that we just talked about, and that's what this standard's used to kind of evaluate. Whereas for foot-transmitted vibration, currently we don't have an international standard specifically for assessing health risk for the feet. What we actually use right now is the whole body vibration standard. So it's considered to be applicable to motions transmitted to the human body as a whole through the supporting surfaces. So these would be considered the feet of a standing person, the buttocks, back, and feet of a seated person, or the supporting area of a recumbent person. So at this point, it's not necessarily clear that this standard is the most appropriate for evaluating health risks to the feet, as it's kind of used for it's typically used for seated operators. And then it also evaluates things like motion sickness, nausea, and there's specifics for lower back pain in this standard. So we've progressively continued to see an increase in foot-transmitted vibration exposure. By taking the tools, we're mechanizing a lot of things underground, taking tools out of people's hands, and now they can actually rest them on things like bolting platforms or raised platforms. So this is just a mock-up of a jack leg on a bolting platform or a raised platform. And then we've also started to use more bigger equipment with jumbo drills. So although the operators don't actually have to hold the pieces of equipment in their hands anymore, the entire platform underneath them is typically vibrating. And this is just a summary of some of the previous literature that we've seen for foot-transmitted vibration. So a study with jumbo drill operators, 3 out of 5 of the operators reported moderate to severe pain, aches, or discomfort below the knees. For bolter operators, Thompson and colleagues completed a case report where a 54-year-old miner had a chief complaint of blanching and pain in the toes, so kind of like what we saw with the blanching and the whiteness in the toes. And then for drilling platforms, it's been found that 6 out of 27 miners, so this study was actually in 1989, had experienced numbness and blanching again in their feet. So it is becoming more and more of an issue. As we're all interested in occupational health and safety, I thought that maybe if we talked about how you would apply the hierarchy of controls to the foot-transmitted vibration. So if we were to start trying to design possible prevention strategies, what would that kind of look like if we applied the hierarchy of controls to this hazard? So we'd start with elimination. Can the exposure be eliminated entirely? So do we actually have to use this piece of equipment? Substitution, is there another piece of equipment or tool that can be used? So do we have it in the budget to get something that maybe we can operate remotely where the person doesn't have to be directly in contact with the platform? As far as engineering controls, we could look at jack legs or platforms for isolation. Administration, these would be things like job rotation, taking scheduled breaks, implementing stretching programs. And then for personal protective equipment for the feet, we'd be looking at things like, can we better design the boots, mats, or insoles to isolate the person's foot? And what would we need to know for designing prevention strategies? So first, we'd have to identify the hazard. So at this point, it's not known how vibrations transmitted through the foot. It's not known what frequencies actually affect the foot the most. And then we also don't know if changes in how we apply pressure on our foot are affecting the transmissibility of vibration through the foot. Even to just get to the second part of this, where we'd evaluate a risk, we're not sure how many measurements are required to capture the foot's response to vibration. We're also not sure where we should be taking the measurements because, again, there's no standard for how to evaluate foot transmitted vibration and where's the best locations to be measuring. And then this grayed out kind of font, this is just an idea for the future. I didn't work on it in my PhD, but it's just what equipment vibrates at the identified higher risk frequencies for the foot. So if we were to fully evaluate the risk, then we'd have to actually ask this question as well. From here, if we had all of this knowledge, then we could start to actually control risk and design better things for isolating workers from foot transmitted vibration. So this is just, again, bringing this back to why would we need to know this? A couple of things we're just going to go through really quickly before we get into my results are the concept of transmissibility. So transmissibility in its simplest form is just a ratio between 2 points. So on this slide, I just used an example where you could take a vibration measurement at the platform and then at one point on the ankle. And if you took those simultaneously, you could calculate the ratio in between those 2 points. If the ratio value is greater than 1, it means that the vibration's been amplified. If the ratio value is less than 1, it means the vibration's been attenuated. So this is just understanding kind of, you're going to see a lot of transmissibility values in my results. And then the other thing I'm going to be talking about a lot is resonant frequency. So this is the frequency that's identified to have the maximum displacement of the structure. So this is why you're at an increased risk for injury at the resonant frequency. So in this example, it's just when we take measurements on the toes, the resonant frequency is where the toes have moved the most. So they've been displaced from the platform the most. So we do know that each region of the body has a resonant frequency, and exposure at resonance is linked with an increased risk for injury. So for whole body vibration, for the pelvis and the lumbar spine, it's at a lower frequency. So between 3 to 5 hertz and 10 to 12 hertz is typically where it's found, the resonance is found. For the hand arm, it's 30 to 50. Fingers is much higher at 125 to 300 hertz. So they're just resonance bands. At this point, it hasn't been systematically identified for the ankle and the toes, but we can guess that from the hand-arm studies that there will be differences at the ankle and the toes. And then the last thing I wanted to take you through was just, we're just going to look at one of the graphs really quickly, and so that you'll know what you're looking at when you're looking at my results. So on the x-axis, on the bottom axis there, we have the frequency. So the frequency in my studies from 10 to 200 hertz. So you're going to see that a lot. You'll see a transmissibility magnitude on the vertical axis. And remember, keeping in mind our concept of transmissibility with the amplification and attenuation. So here I put the line at 1, where anything below 1 means that at that frequency, the vibration's being attenuated by the structure. And then anything above 1, the vibration's being amplified through the structure. if we look at frequencies of amplification, so in this example, let's just ignore the beginning of the signal, and we'll just say frequencies of amplification for this signal were between 60 and 175 hertz. And then if we're talking about resonance, when you see, I'm going to present a bunch of peak values to you. And so when we're talking about resonance, or I say average peak, we're talking about the highest value in the signal. So for this one, the resonance of this signal would be between 110 and 140 hertz. So then exposure at these frequencies would be the most dangerous for the person's foot. So all of this kind of led me to my research questions. So today I'm actually going to go through 3 of my PhD research objectives with you. And the first one's going to be just the first question that we asked was kind of, in our natural standing position, how does vibration resonate in different parts of the foot? So we coupled with a lab in Lecco, Italy. It's called the Metrospace Lab. It's at Politecnico di Milano, or Polimi University. And we had to have, as such, we had research ethics from both universities. We ended up with 21 participants, and their anthropometric information is kind of summarized for you there. The reflective marker setup. So instead of using accelerometers for the study, we used a laser Doppler vibrometer. So in this case, you have to put reflective stickers on the anatomical locations that you want to measure. Chose 24 anatomical locations. So in that image on the right, you're going to see we picked 15 points on the toes. So 3 points on each toe. So the toes are just numbered T1 to T5. Then the point numbers, there's 3 on each. Then we picked 4 locations on the medial side of the ankle and 4 locations on the lateral side, and then 1 location at the back of the heel. So it's just labeled H1. As I said, we used a laser Doppler vibrometer. So you just point it at the reflective marker applied to the skin, and then this is used to record the vertical vibration. So instead of using accelerometers and having to apply them, it's just a quicker way to get the measurements. And then there was an accelerometer on the platform. It was glued to the platform just to take, like I said, to get the transmissibility measurements. You measure the platform and then one of the locations simultaneously. So the actual exposure profile, it was a sinusoidal sweep signal, and then the frequency range was 10 to 200. We kept maintained the magnitude the same, so that just means the platform magnitude, and it was just at 0.5 meters per second squared. So what the participants would do would be they'd step on the platform and we'd point the laser at one of the locations. They'd have a 51-second exposure to get through that entire sweep signal. Then they could take a 10 to 15-second rest period after, and then we'd repoint the laser at the next location. Overall, the actual exposure time for this study was approximately 21 minutes. And so here's what one of the transmissibility results from. So here we're looking at T1, P3, so the metatarsal head of your big toe. And if we, again, so in black, it's the average of the 21 participants. In gray, it's the standard deviation. So if we put the line at 1, and now we're looking at the resonance band, so which frequencies were led to amplification. For this specific location, it was between 40 to 145 hertz. We saw amplification of the input signal. And then we'll look at this if we compare 2 points. So again, the top ones are the one we just looked at, T1, P3, and then the bottom graph is H1. So if we, again, impose the line at 1, and now we look at where resonance was for these 2 locations, you're looking at the first one, 40 to 145 hertz, and around the ankle, or sorry, the heel, we're looking at, it's a much lower frequency from 10 to 35 hertz. So just from this simple example, you can see how different the toes and the ankle react to the same vibration input signal. And then here I just kind of wanted to illustrate, so these are the average peak frequencies and average peak magnitude. So remember on the graph when I showed the peak point, this is just the number associated with that. So in red, you'll see the worst or the highest. So for the toes, the average peak frequency, the highest, it got up to 147 hertz. Whereas for the heel, it was 16 hertz. And just from this overall looking at this data, you could see that the toes are, the resonant frequency for the toes is much higher The midfoot, it's a little bit more in the middle. And then for the ankle, it's a lot lower frequency. And then we had a second research question. So here, how do changes in our center of pressure affect how vibrations transmitted through the foot? So using that exact same setup, all we did was we took center of pressure measurements for all of our participants. So in the middle, you'll see that natural standing where the center of pressure is actually distributed throughout the foot. Then we'd ask our participants, okay, can you try and put the pressure all into your toes? So that's what's considered the forward leaning pressure. And then you'll see a backward where the pressure is concentrated into the heels. And then we ran them through the exact same protocol where we'd take the 24 anatomical locations. And so overall, the participants were exposed for about an hour. And here you're going to see the average peak frequency values. So in the center, we already looked at what was the natural. And then on the left, you're going to see the forward position. And on the right, you'll see backward. So you'll see that when we ask people to concentrate their pressure into their toes, that increased the resonant frequency at the toes. So instead of being at 147, now it gets worse up to 170. And then when we ask people, very similarly, when you ask people to concentrate all of their pressure into their heel, you can see that instead of it be the resonant frequency at the ankle being something like 16, the lowest actually got up to 33. So just when you concentrate the pressure into a certain area, that's going to increase the resonant frequency and the magnitude at that area. And here, you don't have to actually see any of these values. All I want you to kind of look at is the trends of the lines. So this is just, if we're looking at the 15 locations that we took on the toes, for the toes, the peak frequency went up so that, here, can you see the arrow? So you'll see that in the forward lean position, peak frequencies were higher than when you were in the backward lean position. But when we talk about magnitude, it seems to go the other way. So what happens is when you're concentrating all the pressure into your heel, now there's no weight helping push down on your toes. So now they're kind of free to actually move. So they're actually displaced a lot more when we're in the backward lean position, although the frequency gets a lot higher. And this is just kind of a summary of what happened in this study. So we found differences in how vibration was transmitted through the 24 locations on the foot when the center of pressure was shifted forward or backward. And in this example here, you could just see what might happen with one of the ankle locations. So the peak frequency, so along here, didn't change too much. But when we asked somebody to shift their weight backwards, the magnitude difference was almost twofold in how the vibration was transmitted through that point on the ankle. So L4 was actually like the lateral part of the ankle. And then one of the last research questions I'm just going to run through with you is where and how many measurements should we be taking on the foot? Oh, sorry. So from all of the measurements that we took, so we ended up taking over 1,500 measurements. One of the questions was just how can we condense this down and figure out where we should be taking measurements on the foot. It's not practical to be taking 24 every time you want to do some kind of experiment or you want to test insoles or test anything like that. So one of the main questions to kind of come to a conclusion and pick a statistical test was how do we infer risk from transmissibility? So like I said before, transmissibilities of 1, let's consider those to be kind of lower risk, so they're in green. Transmissibilities of 1.5, this means the signal is amplified about 50%, so a little bit higher risk. And then transmissibilities of 2, we're just considering these to be the person's at an increased risk, just because that input signal has now been doubled or it's been totally amplified by 100%. So the method that we used, it's called, you don't need to know anything about it, it's a multiple correspondence analysis. It's a type of statistical test, so if you're super interested in stats, we could talk about it. But it's just a form of geometric modeling with descriptive statistics. So all we did in the simplest form is each of the measurements that we took, so that 1,512 measurements, just evaluated each of them as to whether they were over 2. That 2 threshold was a yes, and if they were under, it was a no. So that's kind of how this multiple correspondence analysis works. So the reason for this is because in statistics, we had only 21 participants, but 24 anatomical locations. So finding significance can be very hard when your number of participants doesn't actually overreach the number of locations you take. So here, this is what would happen in a multiple correspondence analysis. You get these symmetric variable plots, and it's just a way of plotting the locations. But I took these and put them in a more of an anatomical view so that you could actually see kind of what's going on. So here again, we're looking at the forward, natural, and backward center of pressure locations. What we're looking at with the black locations, there was no variability, so these were excluded. So at the T1, P3 at the head of your first toe, your big toe, and then at the heel, at no point did any of these measurements ever reach that threshold of 2. So they're just kind of excluded from the test because there was no variability. All the participants, they never reached the threshold. So then you'll see the different areas. So area 1, 2, and 3. And this just means that at these anatomical locations, at these anatomical locations, the structure reacted the same based on the groupings here. So if we look at the toes to start, you can see that the toes we could actually probably group as one, other than T1, P3. We could probably group those as one location. You'd only have to take a measurement on one toe to get the overall reaction of the toes. You'll see the most variability happen throughout the midfoot and the ankle, where when you actually ask somebody to lean and put all the pressure into their heels, this caused most of the anatomical locations to be almost exactly the same. So they're almost all in red, and you could see that you could take one measurement when somebody's in that position, and it would capture most of the response. So overall, then, where should we measure? That's what we all want to know. In a forward, natural, and backward, I just selected locations based on, so in my master's and my PhD, I've probably taken measurements on over 70 feet, and with an accelerometer or a laser Doppler. And these locations are the easiest to palpate. So T1, P1 is the nail bed of the first toe. So that's actually very easy to find, and you could put an accelerometer on it pretty easily. The distal head of the first metatarsal. So like we said, that T1, P3 location. And then the middle of the second metatarsal, which is just in the midfoot, and then maybe one location on the ankle. So if you took 4 measurements instead of taking 24, you could capture the entire response of the foot. So overall, what have we learned? If we go back to those questions that we asked for designing prevention strategies, from the first study, how is vibration transmitted through the foot? Well, we know now that there's differences in transmissibility based on the anatomical location, with the major differences being here with the toes, midfoot, and ankle. So what frequencies affect the foot the most? At the toes, we found it was approximately 93 to 147 hertz. With the midfoot, 50 to 80. The ankle, 16 to 33, so much lower frequency. Then from the second study, again, what frequencies affect the foot the most, and do changes in how we apply pressure on the foot affect the transmission of vibration? So here's just a summary of all those findings. So I just gave the frequency ranges for the toes, midfoot, and ankle in all of the positions. But the major finding here is that wherever you ask somebody to concentrate their center of pressure, their resonant frequency is going to increase. So whether you ask them to concentrate it in their toes, the resonant frequency is going to increase in the toes and midfoot. If you ask them to lean backwards onto their heels, resonant frequency is going to increase in their ankle at the heel locations. And then from the third study, how many measurements are required to capture the foot's response to vibration? So regardless of the center of pressure location, you're going to need probably 4 measurements. And then we now know where those should be. They should be on the nail bed of the first toe, distal head of the first metatarsal, middle of the second metatarsal, and then the lateral malleolus. So what does this actually mean for the future? So if you're in a lab and you're a researcher, then for you, this would mean decreased exposure time. So now we can test different conditions using the same participants. So you could test different insoles, you could test different postures, people standing in different postures. So you don't necessarily have to test just somebody standing in a normal posture. That might not be how they work. So people might actually be in more of a lunge position, and you could do testing like that because you have less measurement locations to take. So this is also going to lead to a lot of increased success with our ethics applications when you're not exposing people to a lot of vibration, the ethics boards like that. Your foot, we also learned your foot cannot be treated as a single component. So we can't look at the foot as just a one single structure. It's all going to react the same. So this will be helpful for our design engineering when we're talking about solutions development. So for example, if we're talking about designing an insole, having an insole that just has one stiffness and damping component throughout is probably not going to be sufficient because we know the toes and the heel react differently. And then as far as modeling, so eventually we don't want to have to expose participants when we want to test insole characteristics or boots or mats. So for modeling, again, you can't represent the foot as just one structure. It's probably going to have to be at least two. And then in the field, as ergonomists or occupational health and safety specialists, remember one of the questions that I had in gray was we need to update foot transmitted vibration field exposures. So taking measurements just on the platform, and those are measurements that we do need to update so that we know what frequencies people are being exposed to. So if people are never being exposed, let's say over 100 hertz, then we don't have to design prevention strategies to isolate over 100 hertz. So that's why it's really important to be able to match those with what we now know happens at the foot. Then we can also maximize our risk analysis. So we only have to measure at known locations for increased risk. So you don't actually have to measure 24 locations to measure this properly. And then there's the potential for a new standard for evaluating foot transmitted vibration instead of grouping it with standing whole body vibration. So like I said at the beginning, when we are talking about what standard is currently being used, we only have the one international standard that's used for seated people and standing people. And so this would kind of indicate that eventually we're going to have to separate those two out. So just a couple of acknowledgements. I'd like to acknowledge my co-supervisors for my thesis, Dr. Tammy Eager and Dr. Brent Levers. I had some graphic design help from Leah Hodgson, so she's a science communications officer with Crosh. All of the help that I got with the equipment and data analysis from Politecnico di Milano with Dr. Marco Terabini and Francesco Corti. And then all of the financial support that I receive from NSERC, the Goodman School of Mines, and the Center for Research on Occupational Safety and Health. So I'd like to open up the floor if anybody has any questions.
Just out of curiosity, steel toe boots. I know it wasn't part of your research, but
Yep.
if you had a guess, I mean, I would assume that it would definitely the steel toe would actually have a large influence on the transmission, or?
Absolutely. So we are doing some testing of boots. At this point, it's hard to test the full boot. You can't test the full boot with like a laser Doppler because you're pointing it down. But the component in the steel toe component in the front adds to the weight. The boots also, if you've ever worn like a snowboarding boot, we're also testing the difference. So all of my measurements were with barefoot participants, but there's that heel component that actually makes the foot rock forward a little bit. So now you're putting more pressure on the toes. So that's also something we're going to be looking at in the future as well. But you're right, it would definitely change the transmission. It changes the weight, the way that you distribute the weight in your foot, and it's something that we are looking at. I think right now we've only kind of evaluated them for comfort, which boots the people like the most. So I think we had one student evaluate 4 boots for the different comfort and see which ones people like the most and found the most comfortable. But it was a black leather looking boot. That's a good question, Trevor. Thanks.
And I have a couple of online questions. One's a little bit old, so you may have addressed it, but I'll read it out anyway.
Sure.
Does FTV include vibration through foot pedals in trucks?
Definitely. So, at this point, that's also lumped into seated vibration. So we don't often, when you're taking a vibration measurement, you don't often take it at the foot pedal, but that is an exposure contact point, absolutely, at the pedal.
And the second question is, can we assume that body structure will also affect this study? For example, 5 foot versus 6 foot, and weight.
Yeah, anthropometrics definitely affect how vibration is transmitted, specifically for seated people at this point, seated operators. So you would know if you are a 5 foot tall woman sitting on a seat versus like a 6 foot tall man, like you used in this example. There will be differences in how much vibration is transmitted to you through the seat and where you specifically are attenuating the vibration or amplifying the vibration. But in this study, we didn't have enough participants to have any kind of statistical significance in, there were 7 females and 14 males, and there wasn't enough to evaluate those separately.
Thank you. Any other questions?
Just wondering if there is any equipment what we could take out to the field to help to do some measurements, or this is strictly lab measurements?
So in the field, what you would take out is you could take one accelerometer and just do the measurements at the platform. So you wouldn't have to specifically putting measurements on the feet. Our lab has those kind of small accelerometers, but if you were ever going to do field measurements, it's a much bigger accelerometer, and you would just put it on the platform as close as reasonably possible to somebody who's working without damaging it, and you'd take a measurement like that. But you don't need a laser Doppler or anything like that.
Yeah. I'm Tammy Eager with Crosh.
My
so
supervisor.
This isn't fair. This is a pre-defense question for Katie. So thanks for the presentation. I thought maybe you could talk to the audience a little bit about how the vibration travels through your body differently at those different frequencies, because I think that's an important concept. So you talked about your exposures between 0 to 200, but you don't feel all the vibration just at the feet. So maybe you could just talk a little bit about what it feels like at those different frequencies and how that might affect injury at different part of the body.
Sure. So if you've ever stood on those vibration platforms in the gym, for example, my master's study, we used a vibration platform from the gym, and it actually only vibrated from 10 to 50 hertz. So what happens is when you run through a spectrum like that, you're going to feel the vibration resonate at different parts of your body. So for instance, when you're standing on the platform, you might not actually feel it at all in your feet, but all of a sudden your eyes at about 30 to 40 hertz, your eyes are jiggling and you can't see anything on this platform. So these are kinds of, when you're being exposed to vibration, you're going to feel it in different parts of your body. You might feel it in your lower back, especially standing. So when you increase the stiffness, a lot of times what we ask people to do is kind of bend their knees. If you were to stand on the platform ever with your knees totally locked, then you're actually just letting the vibration shoot up to the back of your neck and into your head. So all of a sudden you're going to feel it, and there'll be a lot of tension there. But it is very different for every person for how they can stand. And on the platform specifically, just maintaining your balance can sometimes be difficult if you've never stood on something vibrating like that. And so in our study, it was actually student participants. So they weren't occupational, like people who had been exposed daily. So learning to balance in that first little bit is actually kind of difficult. It's a good question.
And I think Kimberly saw, if you don't mind confirming, I think Katie just answered your question. Are there any others in the audience? And Kimberly, if you could comment, I think Katie just got your question answered. Anything else from the audience?
Just wondering if custom orthotics that you set up for different injuries in the leg, would that benefit the vibration or would it amplify?
Okay, so custom orthotics. We are actually testing a bunch of different insole materials with Vibram. So we're working with that lab in Italy, and they have a partnership with Vibram. We're testing different insole materials, and the way that custom orthotics actually would fit your arch, and that would be a really interesting. We haven't looked at that yet. We've just looked at like a one size kind of fits all, very flat material, and how that would attenuate a vibration signal. But we haven't looked at the custom ones just yet.
So this will be a bit of a plug here for OCOW too. So if we do have workers that are thinking they're experiencing problems from vibration or vibration-induced whitefoot, what do you recommend? What should they do? Obviously, they could contact OCOW, and but what are some other recommendations in order to try to make sure that this doesn't turn into a situation like we heard from the founder of RSI, where your issue becomes so severe that you become and have a permanent disability? So early symptoms, just remind us what those are, and what are some recommendations for people?
Sure. So the early symptoms are going to be those neurological symptoms. So this is going to be that the neurological ones will come first. So these are often the numbness or the loss of sensation. And you'll see these, or you should kind of feel these before you would see the blanching. So by the time it's been blanching, you've been exposed for a bit. So neurological symptoms first is what you'd see. If at any point you're kind of experiencing this kind of numbness or that kind of sensation when you're on anything that's vibrating, obviously report it to either your Joint Health and Safety Committee personnel or your occupational health and safety special, like whoever in your company that you're reporting to. And then from there, if you're an actual worker, some of the things that you can do would be to try and keep your feet and hands as warm as possible. So if they're getting cold, a lot of these symptoms are actually mistaken for frostbite. And so if any of your periphery is getting cold, you got to keep it warm to increase the circulation to those areas. And then at the same time, trying to keep it as dry as possible. So this could be hard in underground mining. It won't be hard to keep it warm, but it will be hard to keep it dry. And those are a couple things you could do. You could take breaks. So those administrative controls that we talked about, taking more breaks if you start to feel any kind of symptoms, take a break, let the symptoms dissipate, and that's kind of how you would deal with that initially. But definitely reporting the symptoms, reporting them to your doctor is kind of where you would go. Go ahead.
The gym platform, how safe are they?
It's a loaded question. So the safety, they're safe. It's prolonged exposure that's going to cause any symptoms for you. So typically the gym platforms, they're set to go for 60 seconds, and we use them for experimenting with people, and you could totally go on those for 60 seconds at a time, as long as you're not on it for 12 hours a day doing anything. Again, if you are going to use it, I would encourage you never to keep any of your body parts rigid. Try not to get as much vibration to your head as possible. But as far as we do use them for testing, and just don't use them for prolonged periods of time or probably every day.
Thank you.
Thanks a lot, Katie. When I first heard that Katie was going to be doing her research on vibration whitefoot, I was at the meeting when she was talking about it. I kind of perked right up, because I've been arguing for 20 years about vibration whitefoot, the fact that there is so little research actually out there on it, and as a result, getting it compensated is much more difficult because you don't have that research out there. So what we heard about today, in terms of our motto of moving forward, this is research moving forward. This is groundbreaking stuff that is going to set the pace for the recognition of this disorder down the road.